Hey everybody, welcome back to the channel. We're looking today at slopes in context. This is kind of going to be an exploration of velocity and acceleration, and we're going to start by looking at the position stuff we've been talking about. And believe it or not, all these things are actually related to the idea of a slope that you've been talking about in your math class, and specifically a slope in context of a situation. So slopes in context, like the slope is the change in y over the change in x. And when we talk about context, what we're saying is that x and y have values. They have been assigned things like time or position, velocity, etc. So a normal situation doesn't really have a context when you're just like solving a basic math problem. But if you apply something like, say, time and distance, you've created a context for the slope. You've made it to where the slope has a meaning that goes beyond the change in y over the change in x, because the change in y means something. And the change in x means something. So let's take a look here at the situation of a position versus time graph. So we have position on the y-axis and we have time on the x-axis. Since position is on the y, then the slope in this case would be the change in position over time. That has the phrase of speed or velocity. Okay? So when we're looking at a position versus time graph, the slope of that graph is velocity, or speed if we're not talking about a vector situation. But for the most part, we're going to be looking at vectors from now on. So in this particular case, we have a horizontal thing. And as a result of a horizontal graph, what's going on here is that the object isn't moving. The position is remaining at 4 meters from the reference point the whole way through. In this case, minutes. So for 6 minutes, this object has sat at 4 meters from the reference point. Okay? Because there is no change in y is 0. The slope of this is 0, and we say that it's not moving. The velocity is 0. But if instead I have a straight line, then the slope is still determined by the change in y over the change in x. Now I can say that there is a change in y. In this particular case, we're changing y by 3 meters every minute. So the velocity of this particular object is 3 meters per minute, which isn't very fast. But maybe we're looking at a turtle. I don't know. There's lots of different things that could be moving from a different position. The important part here is that the slope of this line is the velocity. Now in this case, we have a curve. This is actually a quadratic equation. This is the quadratic equation y equals 2x squared. Okay. Now when you're looking at a quadratic or an exponential or any polynomial of this sort of thing, this sort of type, where you have a curve and not a straight line, then the velocity or the slope is changing. Okay? Slope is changing over time, which makes sense. If you look at the bottom of this, if you look towards the 0, 0, going up to the 2 on the x-axis, you can see that there's this curve, and the slope is changing. And if you look from like 2 to 3, the slopes become a little bit different. And 3 to 4, the slopes become a little bit different. 4 to 5, the slope's a little bit different. Every single time period we look at, the slope's a little different than the last. The slope is becoming increasing, actually, as it goes. So this concept gives us an idea of a velocity that is changing. Now, when a velocity is changing, we say that the object is accelerating. So, in the previous cases, velocity was constant. When velocity is constant, then in the first case it was 0. In the second case it was like 3 or 4. The slope of the line, right? If the velocity is changing, the slope is changing, then it's accelerating. In the previous cases, we had no acceleration. So velocity is the slope of a position versus time graph, okay? Oftentimes we're talking about it in terms of like meters per second or miles per hour. However, acceleration occurs when velocity is changing. Acceleration is the change in velocity over time. In other words, acceleration would be the slope of a velocity versus time graph. So if we go back and we look at the position versus time graph and we graph the velocity versus time for that graph, that's what we have here. So the position versus time graph for a horizontal case, this was the original one we were looking at. The position's 4 meters, and it's just hanging out. Well, the velocity is 0, because the slope everywhere is 0. So if I were to graph that, I would graph a line at 0. So the graph that you see below the position versus time is the velocity versus time. Now notice that we have, and there's a slight error on that graph, it says meters per second. It should be meters per minute, because it's the velocity of the other graph, right? It's coming from the first graph. So you'd have velocity in meters per minute on the y-axis, and you'd have minutes on the x-axis. So what you actually have is meters per minute per minute. Meters per minute, or meters per minute squared. Now you've seen this in your F equals MA work, and you've seen that we had meters per second squared. This is a similar unit. Acceleration has this time squared property, and a lot of kids use that property wrong. They look at the meters per second squared and they think it has to be telling them to do something with the math. And it's really just describing the units of this particular graph here. Because the acceleration is the slope of the velocity graphs. So if we go to the second case where we have the position versus time moving as a straight line, then the slope is constant. It's a positive number. It's not 0 now. Slope is constant in this particular graph. That slope was 3. Okay. 3 meters per minute. But the slope of the velocity graph is 0. That means that the velocity is not accelerating. Velocity is not changing, which makes total sense because the velocity is constant. So once again, we see that we have this case of meters per minute, or meters per minute squared in this case, and we are not accelerating. There's no slope for the second graph. The slope's 0. When we take it to the next case, the changing velocity case, there's actually a cool math thing you can learn to do later on in your career where you can actually find the slope of a line like this. It turns out that the slope of a quadratic would actually give you a linear slope. That's something you'll learn about in calculus. You don't need to worry about how we get there. But just trust me that the graph here, and you see the velocity versus time graph, would be this graph of the slope of a quadratic position. In this case, it's the line y equals 4x. That's what the slope would be, or that's how you'd calculate the slope for the graph y equals 2x squared, which is how the position was moving. Now, because we have a linear graph for velocity versus time, we're going to have a slope that is not 0. In this case, that slope is going to be 4 over 1. The velocity is increasing by 4 meters per second, or meters per minute, every minute. The velocity is increasing by 4 meters per minute every minute. That's what's happening inside to the velocity. That means the velocity is accelerating. Velocity has a slope that isn't 0. So velocity is increasing over time. That's what acceleration means. Now, keep in mind, we've been talking a bit about this idea of a vector, that we can have both direction and magnitude. So when we're discussing these things, it's important to understand that not only could the magnitude increase, which would be reflected in a graph, be reflected by the slope, but you could also have a change in direction create an acceleration. You might have felt this if you've taken a turn on a car. Usually if you're turning on a freeway, you might feel a pull as you're like accelerating into that turn. And that's because you're changing your velocity. So even if your magnitude of your speed remains constant, turning around in a car is actually changing your velocity because you're changing the direction of the velocity. So spinning around in a circle, even if you maintain a constant magnitude or speed, is an acceleration of your velocity because you are changing the direction of the vector. That's about it for this. Hopefully it clears up a little bit about what velocity is. Acceleration is a change in the velocity. Acceleration is a change in the direction or the magnitude of the velocity of an object. Hopefully that's become a little more clear and you have a bit more of an understanding of what that means. And I'll see you guys in class tomorrow. Have a great night.